Okay, so in this video, we're going to cover all of section 8.2, which is the bootstrap t-test, all right? So why don't you pause, copy, play. All right, so the idea with the bootstrap t-test is the name is going to give it away. We're going to use bootstrap, so simulation. So eventually we're going to have a sample distribution that we're going to be looking at. And the T is referring to the statistic we're going to be creating a distribution of. So we're going to create a distribution of a T statistic, all right? So we're going to use the statistic capital T, which is going to be the sample mean minus the population mean, or at least our null hypothesis value population mean, all over the standard error, which is going to be S over root n. That's the standard error of X bar as the t-test. So it's the same statistic as the t-test from section 8.1. But we're going to estimate the actual distribution of capital T via bootstrapping rather than assuming T follows a T distribution, okay? And that's because what happens if our data is not very symmetric, okay? Then it's probably not going to follow a T distribution, right? And we're going to look at an example like that in a minute here. So here's the bootstrap t-test. We have some population parameter we'd like to estimate and get some good bounds on, probably mu, but let's just call it theta. We have an estimator, theta hat, so mostly that'll be mu, and that'll be X bar, the sample mean. And we're going to have the standard error be the corresponding standard error. Okay, so we'll have the standard error somehow. We'll have a null hypothesis of the value of the parameter, and the alternate is it's not that. Okay. Here's our observed test statistic. It's theta hat minus theta 0 in the null hypothesis divided by the standard error from our data set. Okay. Then we're going to do 10 to the 4th or 10 to the 5th resamples, bootstrap resamples. So with replacement, so we look at our data, we resample that many people with replacement. We compute our new test statistic. So the sample mean of our resample minus our original sample mean divided by the standard error, the sample mean of our resample. Okay, we'll record that and we'll do it 10 to the 5th times. And I'll create a empirical distribution of T star. Okay. And then the p-value is going to be the proportion of times the bootstrap statistic, the T star, exceeded the original statistic, the observed statistic T. And if it's a two-sided p-value, we multiply that value by 2. Okay. All right. So hopefully nothing surprising here. We've seen things like this in the past. All right. So we're going to be switching over to some R here for this one, right? And this is the last panel for this video. So why don't you pause, copy down what's here at least. I'm going to be filling in some stuff down. Okay. All right. Well, so we're going back to the Bangladeshi wells, the 271, I think it's 271 wells in Bangladesh. We recorded a bunch of chemicals, but in particular, we're focusing on the arsenic levels. And we might have a null hypothesis that the mean arsenic level is 100 parts per billion. And the alternate hypothesis is that it's more, okay? Now, we could, so this is a one-sided alternate hypothesis. So we need a one-sided p-value. So I could do the one-sided p-value just using a t-test from section 8.1, okay? And I'll show you how to do it in R in one fell swoop, okay? But we could use all the stuff we used in section 8.1 to crank it out, getting some of the information from R. In which case, I got a t-value of 1.3988 and had a p-value of 0.0815. Now that's greater than 5%. So this doesn't appear to give us any reason to reject the null hypothesis. It's saying the t-value we saw could well have occurred by chance. So let's stick with the mean arsenic level is 100, right? Now the problem is that if you look at the data, the arsenic data, you'll see it's way right skewed. Okay, it is not symmetric, right? It's very asymmetric. And if you recall, one of the assumptions for using a t-test is if your data is not normal, it'd be really good if it's symmetric. The less symmetric it is, the less likely a t-test will be to do it to create an accurate p-value, okay? So there's reason to have suspicions about that p-value. All right, well, now we're going to look at the same data and do a one-sided bootstrap t-test that we referred to in the previous spot. Okay, and I'm going to switch over to R, and I'm going to show you where this one-sided info came from, and then we'll crank to this two-sided info, all right? Okay, so here is the chapter 8 R file that's on Canvas. You know, my computer is being very fussy today. It is a Monday. Okay, so let's see. Now, under packages, I've got the resample clicked off, which you need to remember to do. And I'm going down here to line 23. Now, this is to do an actual t-test, not a bootstrap t-test, just a straight t-test. T-test, the Bangladesh data set, the arsenic column with a null hypothesis, mu equals 100, and the alternate hypothesis that mu is greater than 100. So if I run that, if you look below, you see a p-value of 1.3988. Degrees of freedom is 271 minus 1, and the p-value is 0.08151. So it does all the t-test work automatically. It even gives you a 95% confidence interval. Okay, and the mean of the sample of 125.3. So that's where I got the information I placed up on the board. Now let's just look at a histogram of the arsenic data. Okay, and you see it's way right skewed. It's got a long right tail and virtually essentially no left tail, which makes sense because it's kept at 0 for parts per million. Okay, so this gives us pause to think that a t-test might be the appropriate test because the data is not symmetric. All right, so now we're going to do the bootstrap t-test starting at line 27. So first I'm going to simplify my data name. I'm going to call arsenic the arsenic column from Bangladesh. I'm going to run this thing 10 to the 5th times, as line 28 indicates. And I'm going to get my observed T statistic. So one way to do it is to define observed capital T. We're defining it via that arrow dash thing again. Is from the t-test, grab the statistic, okay? And I can actually ask, what is that observed T statistic? And that's where I get the 1.398835 that I have on the board, okay? I can also figure out the mean arsenic level, X bar. N is the number of wells, so it's the number of data entries I've got, which should be 271, by the way. And then I'm going to create a vector to store my bootstrap results in. So that's going to be numeric n, so 10 to the 5th long. Okay. All right, so starting at line 35 is where my simulation takes place. So line 37, boot X is going to be sample from arsenic, from that arsenic vector, and entries, 271 entries, and replacement is allowed. Replace equals true. Line 38, I'm going to take the mean of my resample, so that's my X bar for the resample, minus the original X bar, which is now recorded as X bar, and then I'm going to divide by the standard deviation of that, the new X bar. So that's the standard deviation of the boot X data divided by the square root of n, since I'm doing a sample mean of it. Okay, I record that, and then away I go. Okay, so let me run 35 through 39. It might take a while because 271 data pieces, 10 to the 5th resamples, you know, it's not a small process. It's still running, still running, still running. Maybe I should have done 10 to the 4th. I don't know. Okay. Wow, still running. Okay, maybe my computer's really unhappy with me. There it goes. Now it's done. Let's look at a histogram of this thing. It should appear more normal. Okay, a little bit left skewed perhaps. Here's the observed T statistic coming in the vertical line. And now I'm going to ask, let's add up the number of entries that are greater than our observed T statistic, add 1 to it, and divide by capital N plus 1 for my T value, okay? And I get that 0.050839, okay? So I'm going to stop sharing and record this data up here. So 0.0508. Okay. So This bootstrap t-test gives me a p-value basically right on that borderline, okay? Now the original, just the one-sided t-test, gave me a p-value of 0.08, so that was pretty likely to reject the null. Here, I'm really torn on whether I should reject the null hypothesis or not. It is completely borderline. Although maybe with arsenic levels, you know, maybe you want to err on the side of caution. Say, okay, you know, if there's any chance that the average is greater than 100, we should start investigating. So maybe you're going to do a threshold of 90% versus 95%, something like that. But anyway, bootstrap t-test gives us a significantly different p-value. Might not necessarily change our mind about rejecting null hypothesis or not, but it's a significantly different p-value. And this is far more accurate because, as we noticed, our data was not symmetric, okay? So this would be the way to go with this arsenic data. And in general, bootstrap t-tests are quite accurate. So they are generally a strong method to use.